In this video, we're going to make some Taylor polynomials that remind us of the ones that you see here. I have my students memorize pretty much everything in this list, except maybe tangent inverse. And the reason I do is because they can do challenging problems and make Taylor polynomials that aren't on this list just by referring to what's here. To give you an example of what I mean, in this first exercise, we were asked to find a Taylor polynomial for e to the x squared. Well, if you know that e to the x looks like this, it's 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, etc. Okay, imagine all you have to do is everywhere you see an x, just plug in an x squared instead. So e to the x squared would look like this. So right here, where I'm supposed to have x squared, I already have x squared and I'm squaring that. And over here, where I'm supposed to have x cubed, I'm going to put x squared in there first. Dot, dot, dot. Then all you have to do is simplify each power, and you come up with something like this. It's 1 plus x squared plus 1 over 2 factorial x to the 4th, 1 over 3 factorial x to the 6th. And if you do enough of these, you can kind of tell what comes next. Yes, it would be 1 over 4 factorial and x to the 2, 4, 6, 8. And finally, the sigma notation for this would be the sum from n equals, on this one I like to start counting with 0 and go to infinity and write something to the effect of 1 over n factorial x to the 2n power. Now you can write this, but you always want to check to make sure it really returns the items that you had here to begin with. For example, when n equals 4, I get 4 factorial, and 2 times 4 is 8, so that checks out. And what about when n equals 1? Well, here's 1 factorial, and here's 2 times 1. 1 divided by 1 factorial is just 1. And so that matches up well with x squared right there. So that's an example. Now, this next problem asks us to make a Taylor polynomial for x squared times e to the negative x. So you might do this in a couple steps here. First of all, e to the negative x would look like this, except that everywhere there's an x, you'd have a negative x. So that would be 1 plus negative x plus 1 over 2 factorial negative x squared plus 1 over 3 factorial negative x cubed, etc. And as you can see, some of these negatives will stick around because they are raised to odd powers, like 1 and 3 and 5 and so forth. For the ones with the even powers on them, though, the negative won't appear in the answer. So we'll have x squared times 1 minus x plus 1 over 2 factorial x squared minus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th, dot, dot, dot. And then multiply through with x squared, distribute. So x squared times 1, of course, is x squared. X squared times x is x cubed. X squared times x squared is x to the 4th. X squared times x cubed is x to the 5th. And the next one's going to be 1 over 4 factorial, x to the 6th, etc. And the sigma notation for this is going to be the sum from n equals 0 to infinity of Well, you're going to have to divide by n factorial. But you're also going to have to do something to get the positive, negative, that strictly alternating look that you see there. And the way to handle that is to use -1 to the n power. Try it out. When n equals 0, -1 to the 0 power is +1. When n equals 1, -1 to the first power is -1. So that'll take care of that. And then finally, we have x to the n plus 2. Right, so for example, our indices go 0, 1, 2, 3. Right here where n equals 3, 3 plus 2 matches with the 5. So we did that one right. Okay, this one asks us to find the sine of x cubed. So it's good to remember that sine is, well, I'll just show it to you quickly here in case you don't remember. It looks like x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, and so forth. Has odd powers, strictly alternates, and does divide by factorials. So you can write something like this. Saves you a little bit of time. And then just drop the x cubed in there and make your adjustments by multiplying exponents. So I'm going to have x cubed minus 1 over 3 factorial x to the 9th plus 1 over 5 factorial x to the 15th. What would come next? Well, yes, it would be minus. It would be 1 over 7 factorial. See, 3, 5, 7. It would be x to the, well, these are increasing by 6 every time. And so the next one will be 21. And it's important to know that because when it comes time to write the sigma notation, you have to have that in mind. So this is going to be the sum from n equals 0 to infinity of, you're going to have to divide by 2n plus 1 factorial. How did I know it was 2n plus 1? Well, because these factorials are moving by 2. Okay? Also, I'm going to have positive, negative, just like I did last time, and that's often, not always, but usually handled pretty well by going -1 to the n. And then as far as the powers of x, it has to have something to do with 6n, because these are separated by 6, every one of them. So plug 0 into here. 6 times 0 is 0. And then add 3. And then see if that doesn't do the job. Go to n equals 1. Let's just test this out and make sure it's really working. -1 to the first power is -1. I've got my minus. 2 times 1 is 2 plus 1 is 3. I've got my 3 factorial. 6 times 1 plus 3 is 9. I've got the 9th power. And just because it worked on one of these terms, it doesn't mean it'll work on the next, but it probably will if you did it right. So you can go ahead and verify for yourself that when you plug in n equals 2, you get a positive here, you get 5 factorial there, and 2 times 6 is 12 plus 3 makes your 15. If it works on 2 of the terms, it probably works on the rest of them. Okay. I think I'll skip the cosine one. It's very similar to what we just did. Let's take a look at this one. 1 over 1 plus x squared. Well, if that reminds you of the very first Taylor polynomial in this chart, yeah, that's the geometric series. Except this doesn't have a minus sign, and it's got x squared. Well, that's okay. What I'm going to do is write down the Taylor polynomial for the geometric series, which is just 1 plus x squared. But instead of writing x's, I'm just going to leave some voids like this. And then how do I handle the minus sign there? Well, you just have to rewrite this as 1 over 1 minus negative x squared, because that's equivalent to 1 plus x squared, and then negative x squared is what's going to go in each one of these voids. So you put negative x squared here, negative x squared there, negative x squared there, etc. And then you just work it all out. So this is 1 minus x squared. It's minus because you're not squaring the negative. But here it's going to be plus because you are squaring this negative, and 2 times 2 is 4. So you'll have x to the 4th. Okay, on this one you're taking a third power of something that's negative. That square doesn't apply to the negative. So the negative will appear. You'll have minus, and you'll have x to the 6th. So the pattern's pretty easy now, isn't it? It's positive, negative, positive, negative. Next is going to be positive. X to the 8th minus x to the 10th, etc. Dot, dot, dot. And the sigma notation for this is going to be the sum from n equals 0 to infinity of negative 1 to the 0 power. We can test to make sure that's going to work. Not to the 0, excuse me, to the n power. And then times x to the 2n power. Test it out, make sure that works. For example, if n equals 3, so the index has gone from 0 to 1 to 2 to 3, that's 4 terms into this, and negative 1 to the 3rd power is negative, and 2 times 3 is 6, so it gave us that term correctly anyway. Okay, finally we have natural log of x divided by x. This one looks pretty easy, but let's give it a shot. You recall that the polynomial for the natural log, which you probably saw in the previous video, is one that is expanded around x equals 1. So it has binomials like this. And actually, let me alter this problem here. Let's do, instead of the one they're asking us to do, let's do natural log of x plus 1 divided by x. Okay, so natural log is supposed to be x minus 1. Minus 1/2 x minus 1 squared plus 1/3 times x minus 1 cubed plus, etc. And where the natural log Taylor polynomial is supposed to have an x, I'll put an x plus 1 there. Hopefully I left enough space for that. And then so you can see what's going to happen is all the 1s and minus 1s are going to cancel. And don't forget this whole thing is divided by x. So we have x minus 1 over 2x squared plus 1 over 3x cubed minus 1 over 4x to the 4th dot, dot, dot. This is all over x, which is going to just drop the power of each one of those terms. And our final answer will look like this. It'll be 1 minus 1/2 x plus 1/3 x squared minus 1/4 x cubed. And the sigma notation for that is going to be the sum from n equals, I'm going to start counting with, well, it doesn't really matter what you start with there. I think I'll start counting with n equals 0 and go to infinity. And then I'm going to need negative 1 to the nth power to get it to go from positive to negative, etc. And then I'm dividing down here by 1 and 2 and 3. Each one of those is 1 larger than the index of the term. So if this is the 0th term, you're dividing by 1. If this is the first term, you're dividing by 2. If this is the second term, you're dividing by 3, and so forth. And that was my choice, to start counting with 0. So down here, I'm dividing by n plus 1. And then the powers of x are just x to the n. x to the 0, x to the first, x to the second, x to the third, and so forth. I think I'm going to conclude the video here. My name's Eric. Hope you enjoyed this. Have a great day.